Space never ceases to amaze us with discoveries that challenge our understanding of the universe. One such revelation comes from the Kepler-51 system, located 2,400 light-years away in the constellation Cygnus. This fascinating system is known for its trio of super-puff planets, gigantic worlds with densities as light as cotton candy. These unusual planets have intrigued astronomers for years. Now, the James Webb Space Telescope has detected a fourth planet, dubbed Kepler-51e. What does this mean for our knowledge of planetary formation, and why is it so significant? In this video, we'll explore the mysteries of the Kepler-51 system, the science behind its unique planets, and what this discovery reveals about the universe. The Kepler-51 system stands out among known exoplanetary systems. Unlike most exoplanets, the three previously identified planets, Kepler-51b, Kepler-51c, and Kepler-51d, are both massive and remarkably lightweight. Their densities are so low that they are often described as cotton candy planets. Though similar in size to Saturn, their masses are only a few times that of Earth, resulting in densities as low as 0.1 grams per cubic centimeter. To put it in perspective, if a planet of this size were placed in water, it would actually float. Scientists theorize that these planets have small rocky cores enveloped by massive atmospheres primarily composed of hydrogen and helium. However, their existence challenges current models of planetary formation and survival. Given their proximity to a young radiation-intense star, their atmospheres should have been stripped away by stellar winds long ago. Yet, they remain intact, defying expectations and raising questions about how such planets form and endure. The recent discovery of Kepler-51e deepens the mystery. Unlike the previously known superpuffs, Kepler-51e has not been directly observed transiting its star. Instead, its presence was inferred through its gravitational influence on the orbits of the other planets, a phenomenon known as transit timing variations, TTVs. Based on available data, scientists estimate that Kepler-51e has an orbital period of approximately 264 days, placing it near the system's habitable zone. The journey to this discovery began with an attempt to observe the transit of Kepler-51d using the Webb telescope. When planets pass in front of their stars, they cause a temporary dip in brightness. By analyzing these transits, scientists can determine a planet's size, orbit, and composition. However, during Webb's observation, something unexpected occurred. Kepler-51d's transit happened 2 hours earlier than predicted. This discrepancy was too significant to be explained by minor errors in the model. Researchers hypothesized that an unseen planet's gravitational pull was influencing the orbits of the known planets. To test this theory, scientists analyzed data from various sources, including NASA's Kepler and TESS missions, the Hubble Space Telescope, and ground-based observatories. By comparing these observations with existing models, they identified a four-planet configuration that accounted for the observed irregularities. This new discovery raises exciting questions about planetary evolution, atmospheric retention, and the potential habitability of exoplanetary systems. Could Kepler-51e be another superpuff, or does it have a different composition? What does this mean for our understanding of planetary formation in extreme environments? As we continue to push the boundaries of space exploration, findings like these remind us how much we still have to learn about the cosmos. Astronomers have identified Kepler-51e as the fourth planet in the Kepler-51 system, with an orbit slightly larger than that of Venus in our solar system. What makes this discovery particularly intriguing is the method used to detect the planet. Rather than being observed through a traditional transit method, Kepler-51e was discovered via transit timing variations, TTVs, a technique that detects exoplanets by analyzing the subtle gravitational effects they have on the orbits of neighboring planets. Adding to the intrigue, Kepler-51e's orbit places it near the habitable zone, raising questions about whether it might possess unique characteristics distinct from the well-known superpuff planets in the system. Could Kepler-51e exhibit features that set it apart from other low-density exoplanets? And what insights does its existence offer regarding planetary formation and evolution in systems like Kepler-51? Exploring other extraordinary exoplanetary systems. The Kepler-51 system is just one of many offering remarkable insights into planetary diversity. Consider the TRAPPIST-1 system, located about 40 light-years away. This fascinating star system hosts 7 Earth-sized planets, 3 of which reside within the habitable zone, where conditions could support liquid water. While none of these planets are classified as superpuffs, their compact orbits and diverse characteristics make TRAPPIST-1 a key system for studying planetary formation and the potential for life. Another compelling example is Kepler-52b, a super-Earth identified by the Kepler mission. Positioned in the habitable zone of its host star, this planet's size and location make it an exciting target for studying atmospheric composition and habitability. Kepler-22b highlights the incredible diversity of planetary environments, even among planets that fall into the same general classification. On the other hand, P-67b bears a stronger resemblance to the superpuffs of Kepler-51. This gas giant is so low in density that it challenges existing theories on planetary formation and atmospheric retention. Like the Kepler-51 planets, P-67b serves as a reminder of how complex and extreme exoplanetary systems can be, especially under intense stellar radiation. The next steps in understanding Kepler-51e. The discovery of Kepler-51e marks an important step in planetary science, but many questions remain. Observing its transit will provide crucial data on its radius and density, helping scientists determine whether it is indeed another superpuff or a completely different type of exoplanet. Additionally, spectroscopic studies of the known superpuffs in the system could reveal their atmospheric composition, shedding light on the processes that shape these unusual worlds. Every new planetary discovery expands our understanding of the cosmos, revealing the incredible complexity and diversity of worlds beyond our solar system. As we continue to push the boundaries of exoplanetary science, findings like Kepler-51e bring us closer to answering fundamental questions about planetary formation, evolution, and habitability. Thank you for watching. If you enjoyed this deep dive into the Kepler-51 system, be sure to like, subscribe, and stay tuned for more exciting explorations of the universe. Until next time, keep looking up. Rocket sparkles.